I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 1 with the course code PHY 212, we are at the lecture number 19 and the topic is the Hilbert space. Hilbert space is a linear vector space which is defined after a mathematician called David Hilbert. It is a collection of functions. That's why it provides a mathematical structure to quantum mechanics. In today's lecture, we will learn that how Hilbert space is defined and what are its basic properties. We start with the basic concept of a vector space. In vector space, the word space means collection or set of different objects. These objects could be some numbers or it could be even some functions. In Hilbert space, we will see that these objects will be some state functions. And vectors are the elements of this space. We call it a vector space because it is a linear or it can be added, or the elements of that space can be added. In order to understand the definition and structure of a vector space, we go back to a mathematical definition of vectors from school physics. You remember that in school, a vector in Cartesian space is a set of three numbers. That is, we can expand the vector into three components. And because of the three physical dimensions, we use three components x, y, and z. So imagine this vector v, which is a member of some vector space, and let's call it a v, and it is expanded into three components, that is ex, ey, and ez are the unit vectors, and it is expanded in terms of these unit vectors, and these vx, vy, and vz are the coefficients or contributions of this vector v along these axes. Now we say that these three vectors, that is ex, ey, and ez, these unit vectors are actually making this vector space, or in other words, we say that these three vectors span the vector space. So now because of two major properties, that is these elements can be added and there is a length or a norm exists, we say that these three unit vectors actually constitute a vector space. If we go to the geometrical representation of this vector space, so you remember that these are the unit vectors in three dimensions, that is ex, ey, and ez, and this is a vector v. So we can expand this vector v in terms of these three unit vectors. So then we will find out what is the component of vector v along y direction and x direction and z direction. So we say then that this whole vector space is spanned by only three unit vectors, and any element of this vector space can be decomposed or expanded along these three unit vectors. So as I said that there are two major properties for some space or some set or some collection of objects to become a vector space. The first of them is the inner product. So we see that if there is existence of inner product on this vector space, so linearity is already checked. So we know that we can add these vectors, but then the second property or the most important property we want to check, is there any inner product, or in other words dot product is existing, and it is defined by if we have two vectors, let's say u and v, so we take dot product between them like this. So in terms of the unit vectors, when two unit vectors, same unit vectors get multiplied, this is equal to 1, and when different unit vectors get multiplied because of the orthogonality condition, then they vanish. Therefore the dot product of two vectors in some vector space is of this form. And then, as I said, the other important property of any vector space is the length of any vector. So we also want to check that the length of a vector can be calculated in this vector space or not. So length of the vector then V is defined by its inner product with itself, and the under root is because to remove the square. So now we know that any collection of objects which has the addition property, that's make it a vector space, or in other words a linearity, and then we go and check for the inner product and the length of the vector. If these two things exist on some vector space, we call or on some space or set, we call it a linear vector space or a vector space. So now next we go towards Hilbert space and see if it has a structure of a linear vector space. Since it is a space of functions, or it is a collection of functions, so there must be linearity satisfied, and also the first condition is that it is a linear. So linearity is satisfied. So we will check that if some space is satisfying linearity. Then we will check that if there is a length or norm existing, but we will not stop here. This is why Hilbert space is something bigger than the linear vector space, because it also needs two another properties, and these are the completeness and we also will check for the completeness and convergence. So completeness and convergence are also checked in some linear vector space. If they exist there, we call it a Hilbert space. So let's check one by one all these four properties for the space of functions, and this will provide us the definition of the Hilbert space. So we start with some notations. So it is denoted by H. There are many symbols existing for it, sometimes small h or curly h or scripted h, but here I will denote it by this capital H. And secondly, it is elements of the Hilbert space are functions. So this is the basic difference between a usual linear vector space and between Hilbert space, that Hilbert space is a function, is a collection of functions. That's why we are using it in quantum mechanics, because in quantum mechanics we have wave functions, and usually it is operator mechanics. So our operators act on functions, and these are wave functions. That's why we need some kind of collection or some kind of space which is made of functions. So Hilbert space is a space which is made of functions. And then these functions are called vectors. So the resemblance between vector space and Hilbert space is so close, that's why we call the elements of the Hilbert space, which are functions, vectors. So vectors will be the elements of this space, and then it is denoted by a symbol H. So now we go towards its properties, or remember that these properties are its defining properties, which means that any space which does not obey these properties will not be a Hilbert space. So there are 4 in number. So we will go one by one. The first one is that the space is linear. Here it is important to note that what do we mean by linearity. By linearity we mean two conditions. The condition first is that if we have some constant a, and then we also have some function phi which is a member of Hilbert space, then if we multiply this constant a with this function phi, we will get another function, because this a multiplied with phi will change the phi, and there will be a changed function. And if this changed function also exists in H or in Hilbert space, for example this a phi is also a member of H, then we say that the first condition is satisfied. So as I said, there are two conditions for linearity. The first condition is satisfied when then a phi is also a member of H. So if you multiply any function of a Hilbert space with any constant, and the resulting thing is also the element of H, we say that the first condition of linearity is satisfied. But there is also a second condition for the linearity, and that is if we have two functions, let's say call them phi and psi, and these are the members of Hilbert space H, and if we add them, for example if I add phi with a psi, and I will get a new function which is the combination of psi and phi, and still this new function is a member of Hilbert space H, or it exists in in Hilbert space H, then this is the second condition for linearity. So if any space is holding these two conditions, then we say that this space is linear. Still, there are three other conditions to be checked, but this is the first condition of linearity, that when we have these two conditions satisfied for space of a functions, we say that at least now this space is linear. Okay. So this was the first condition. Now we go towards the second condition of a or second property of a Hilbert space. And as I already mentioned, that there is a very important thing about inner product, that this inner product must exist, because usually in quantum mechanics you will be wondering that why inner product is so important. Because usually in quantum mechanics we deal with the real quantities, and because we want to connect this quantum mechanics with the real world, for this in real world we can measure real quantities, and real quantities will result from the inner product or dot product. That's why this inner product and dot product is so important to exist on some space or some collection of wave functions which we want to use for quantum mechanics. So let's see if there is a definition of Hilbert space on the Hilbert space, the definition of inner product exists. So if we have two members of H, for example phi and psi, these are the two functions which are members of H, and if there is then inner product of them, this is the inner product, this is the bra and this is the ket, and if we multiply them together, this gives us an inner product. So if this definition is there, if we can multiply the two vectors, or we can take the dot product of two vectors or two functions which are members of H, we say that it has an inner product. Or in other words, if for functions in some interval, for example this interval is a and b, if we are working in some interval, then this inner product is defined in terms of this interval. Here you can see that for the Dirac bracket notation, we have also used this usual notation where phi star and psi are multiplied on this interval, and on this interval this inner product or dot product exists. So we say that the second property or the second condition for any space is satisfied. Okay. So far we have checked two properties. The first was the linearity, which had two conditions, and the second is inner product, and we also have now checked that this inner product exists on the Hilbert space. These two properties are also required for the linear vector space. So far the vector space became linear, but now we go further and check another property, the third property of a Hilbert space, which is related to norm or length. So norm or length, and we will also connect this norm or length to the dot product. So for any phi which is a member of H, there is a norm. If this norm exists, which is defined like this, the norm of phi is actually the square of the modulus, or the phi and phi multiplied together. If this norm or length of a vector can be calculated from the this linear vector space, we say that norm does exist there. If this condition is not satisfied, then we will not be using it for quantum mechanics, because physically then we don't have the notion of length or norm or the real quantities defined on this linear vector space. So it is probably mathematically interesting, but physically it is of no use, because we cannot connect then our quantum mechanics or any theory based on this space to the real world. So to connect it to the real world, we need the definition of norm on our linear vector space. Okay. So this was the third property. Now we go towards the fourth and the last property of the Hilbert space, and this is that Hilbert space must be complete. What do we mean by completeness? We mean that any Hilbert space should include all the possible wave functions which could exist. And you will be wondering how we can do this. We can do this by this definition for Cauchy sequence of functions in H. these converge to the element of H, which means if we have some Cauchy sequence of functions in H and we check its convergence, and if it converges to another element of H, we say that the space is complete. So mathematically, a Cauchy sequence of function, let's say phi n, is such that if we calculate the norm phi n minus phi l, and it goes to 0 as n and l approaches infinity. So it means that these two quantum numbers n and l, they are same but different notations we have used. I mean, they are different, but they are same kind of things. If these n and l go to infinity and the difference goes to 0, I mean asymptotically, if you increase the n and l but their difference goes to 0, we say that this Cauchy sequence is there and our space is complete, Hilbert space is complete and it converges. If these four properties now exist together in some kind of Hilbert space, we say that in some kind of linear space, we say that it is a Hilbert space. Now it is time to check examples of the Hilbert space. So first example is these functions. This is the set of functions defined on the interval, this interval, and it is also convergent and they constitute a Hilbert space. And the second example is the set of square integrable functions defined on the whole x interval, and these are these intervals. So these are actually the two examples of the Hilbert space. Okay. So now we move towards the very important property of a Hilbert space, and that is orthogonality, that whether the vector space is orthogonal or not. It is similar to, you remember in our vectors, that there's two vectors are perpendicular to each other or not. For example, if we have two vectors v and u, and if they have angle 90 between them, we say that it is orthogonal. U is orthogonal to v, and if we calculate their dot product, this will vanish. The same condition we use here for the Hilbert space, and we say that if there are two vectors which are at 90 degree to each other, their dot product must vanish. So we use the definition of dot product which is already defined on the Hilbert space to check its orthogonality. So if we must have a vector and there must exist another vector for it which is orthogonal to it, and if it is orthogonal, they are not 0, psi is not 0, phi is not 0, but still its dot product is 0. So we say that Hilbert space is actually orthogonal. And another thing is that the Hilbert space is defined on infinite basis, which means it has infinite number of unit vectors or bases. By basis we mean unit vectors on which it is expanded, or the functions or the vectors or the elements of the Hilbert space are expanded in terms of infinite number of bases. So here you can see this phi x is some wave function which is expanded on the phi n, which are sort of unit vectors for the Hilbert space, and this a n is their coefficients or contribution or weight for any unit vector, and it goes from 1 to infinity. So this is the expansion of the some kind of vector on unit vectors, and these are the coefficients. So these are called actually bases. So the sequence of functions span the Hilbert space. So whenever we have bases or unit vectors for any Hilbert space, we use the word span. By span we mean that any element, any vector which is the element of this Hilbert space will be expanded in these unit vectors. Like in school physics we have a vector, and this linear vector space is spanned by 3 unit vectors, and then any vector can be expanded into these 3 unit vectors. And the sequence of these functions are actually eigenfunctions of Hamiltonian. So also remember that when we act on these functions, these are eigenfunctions of Hamiltonian. If this is not the case, then we cannot connect it to the quantum mechanics. So the basis vectors comprise an orthogonal set, which means that definitely these vectors are orthogonal to each other because these are unit vectors. So we must have in every direction some unit vector, so they must be 90 degree or perpendicular to each other, and their dot product must vanish. So this is the condition in terms of mathematics, that phi n prime is equal to 0 when n is not equal to n prime, but when n is equal to n prime, this is equal to 1. So the phi n is actually here unit vectors. So you can see that we can span a unit vector, a Hilbert space in terms of orthogonal basis. And then their norm can be checked. You can see that the norm is equal to 1. If we multiply same unit vector with a vector, unit vector, then its norm is equal to 1. So we see these are the bases or unit vectors in which this whole Hilbert space is expanded. And then there is an important concept of Chronicle Delta, which is connected to orthogonality and normalization both together. So by Chronicle Delta, this is some kind of a function. So we can combine unit vector and orthogonality in one thing, and this will be done by, for example, we have phi n prime. This is equal to this is the Chronicle Delta, and this Chronicle Delta means by definition that when n and n prime are equal, here you can see when n and n prime are not equal, then it is equal to 0, because then they are orthogonal. And if it is equal to 1, then n is equal to n prime, because then they are same. So they are in the same direction, then we have the result equal to 1, and they are different direction equal to 0. So this defines the orthogonality, and this defines the unit vector, because norm was equal to 1. If you combine both of them into one thing, then this is the Chronicle Delta. So the values of the Chronicle Delta could be, this could be equal to 0 when this condition satisfies, and this could be equal to 1 when this condition satisfies. So it has two values depending on which condition is satisfied. So this Chronicle Delta is an important concept which is used to represent the orthogonality of Hilbert space. And then the last thing is that can we check the projection of a Hilbert space onto a unit vector? What do we mean by this? In usual sense, you know that when we have a vector v, and we can check that what is the projection of this vector v on x-axis and on y-axis. So similarly, we can check the projection of any element of a Hilbert space into a unit vector. So if I draw a diagram over here, you can see that in this Hilbert space we have many unit vectors, that is phi 1, phi 2, phi 3 up to phi 8, and they are orthogonal. You can see the angle between them phi. Although visually it is not there that you see that it is orthogonal, excuse me, but you can see that these are orthogonal to each other. And if we want to check the projection of any unit vector, let's say projection of phi 3 onto the phi, because this is the main vector phi. So the projection of phi 3 onto the phi will be defined by this dot product, and this is the projection of phi 2 onto the phi. So we can check the projection of any element. In this case, these are all unit vectors onto the phi. Like we have a projection of v on the x and y direction. Similarly, we have projection of this phi along any unit vectors. Or we can even check it from any other vector. For example, in this case, to show that an is a projection of phi on phi n, we can form this dot product. First, we can expand this phi into unit vectors a n phi n, and then we can do this dot product thing, that is phi n in bracket notation. This phi n is multiplied with a phi. And since we have expanded this phi like a n phi n, you can put it over here. A n is constant. Remember, in Dirac bracket notation, we could pull this a n outside the bracket notation, because this is just a constant. And since this is equal to Dirac delta function, if you remember, and this Dirac delta function can be dropped because we know it is either equal to 1 or 0, and this n is by shifting property is shift to n, so we get a n prime. So a n prime is, you can see now, is the projection of n prime on phi. So we see that we can define the projection of any unit vector or any vector on a phi. So with this we reach to end, and today's lecture we have seen the concept of a Hilbert space. So in order to define the Hilbert space, or in order to give the mathematical structure to the quantum mechanics, or the geometrical structure, here you can see it is a geometrical structure to the quantum mechanics. So we have unit vectors defined. These are our unit vectors, and it gives now some sort of geometrical structure to quantum mechanics. So what we have done, we have first defined what is vector space and its definition, its requirements, that is linearity and inner product. Then we went on and defined Hilbert space, which is a space of functions, and in this case then we had 4 properties: linearity, inner product, norm, and convergence or completeness. And then we gave 2 examples of them, and then we used the expansion of Hilbert space into the unit vectors or bases, an infinite number of bases. And then at the end we were able to construct this mathematical structure for our quantum mechanics with the help of Hilbert space. With this, I thank you all.